Hey guys, this is Thatcher, and welcome to episode 5 of my DCTL coding tutorial series. In this episode, we're going to be making a DCTL that corrects for lens distortion within your image. I'll admit that Resolve already has a lens distortion effect, but there's a variety of different lens distortion models out there in academia and in research, and I want to give you the ability to implement any one of those into your own tool. So let's follow in the footsteps of my how to code guide. And step one, of course, is going to be figure out what you want to code and flesh out the math on paper. So let's take a look at one of these lens distortion models that I found on Google Scholar and try to implement it. So I found this paper online called Straight Lines Have to Be Straight, Automatic Calibration and Removal of Distortion from Scenes of Structured Environments. And I know this isn't the paper that first introduced this lens distortion model, but here's pretty much the overall idea. We're going to assume that you're given an image that is already distorted by a lens, and we're going to see how far away the current pixel is from the center of the frame. Then we're going to make an estimate of how much further or closer to the center of the frame the pixel should have been if the image were undistorted. Essentially, they're using this polynomial model that's going to start off with an x and y coordinate within the distorted image. We'll multiply it by the amount that's within the parentheses here, in which the user can choose K1 and K2, and then they'll give us some new X and Y coordinates to sample from. I summarized the same math over here for simplicity. What's important to notice is that in a lot of these lens distortion models, we're going to be using a coordinate system in which the origin will be in the center of the frame. Now, typically in DaVinci Resolve, we've been dealing with an origin that's in the top left corner. So we'll have to make that kind of offset so that we're dealing with coordinates relative to the center of the frame. Additionally, we're going to scale the image so that the width or perhaps the height of the frame is set equal to 1.0. This is important because if some pixel is off, like say right here, then I don't want the resolution of the timeline to affect what distance it is from the center of the frame. Next up, given the X and Y coordinates of the current pixel within this coordinate system, we're going to compute the distance that the current pixel is from the center of the frame. We'll call that RD. Next, we'll let the user specify K1 and K2. These coefficients here. We'll compute the value within the parentheses, and then we'll scale our X and Y coordinates so that we can obtain a new X and Y coordinate within the corrected image. All we have to do then is look up the pixel at the new XU and YU coordinates and return that color instead of the current color that was at XD, YD. It turns out that to model most lenses, we only need the first bit of the contents of the parentheses here. Typically, K2 is quite small and can be neglected for the purpose of lens distortion modeling. With that out of the way, we need to know one more thing in order to have any chance of coding this up. If we go over to the documentation, you can recall that we've spent all of our time using this transform function signature, in which the width, height, current X and Y coordinates, as well as the color of the current pixel are provided to us. With this function, we can't access the colors of any pixel other than the current working pixel. That's why Blackmagic Design also provides the second version of the transform function signature. In this version of the transform function, we are given the width and height of the image, the X and Y coordinates of the current pixel, as well as each of the three channels. However, these three channels are provided as these texture types, which allow us to access any pixel within each of the channels. If we look down here, we get a little bit more information. We can extract from each of these three channels a specific position by using this text2d function. Text2d will first take one of the texture objects, then it'll take an X and Y coordinate, and finally return the floating point value that is at that coordinate. These X and Y coordinates, like the input of the function, are on a scale of 0 to the width or 0 to the height. All right, let's go ahead and start trying to code this up. I'm going to go ahead and copy this version of the transform function, and then I will make a new DCTL here. We'll call it DCTL Tutorial 5 Lens Distortion. And I'll go ahead and paste the new transform function in. I've pulled the math back up, and now we can go ahead and start pseudocoding out what we have to do. Like the previous video, I think it makes sense to establish what parameters we need. Next up, let's go ahead and outline our code. Alright, so this much is fairly clear from my write-up on the right. Once we have the undistorted x and y coordinates, we're going to have to transform them back into our original coordinate system, so that 0 is up here in the top left and the bottom right is going to be the width and height. That way we can use text2d to look up the pixel that exists at this coordinate. Alright, I think we're ready to start coding now. Let's start off by filling out this parameter for k1 at the top. Alright, now the user can specify how much distortion they want. In the model, 0.0 represents no distortion at all, and then -1 and +1 correspond to either pincushion or barrel distortion. Now that we've defined our distortion coefficient parameter, I think we have enough information given these 4 parameters provided in the transfer function in order to compute the entire lens distortion model. The first step will be to transform px and py into our new coordinate system. I think the easiest way to do this would be to scale px and py to be in the 0 to 1 range. After that, we can offset these two values so that the center of the frame is at 0, 0. I've written an initial stab at the scaling operation. However, there are a couple problems that I should highlight right off the bat. First off, px and p width are both integers. Py and p height are both integers. As a result, these two divisions are going to be integer divisions. Given that px is always less than p width, this will always evaluate to 0. Let's cast both of these to floats in order to avoid this problem. The second problem is perhaps more of a nitpick. All the way in the bottom right-hand corner, px scaled and py scaled won't actually be 1.0. That's because if the image width is 1920, then the largest value px will reach will be 1919. Likewise, if the height of the image is 1080, then the largest value py can reach will be 1079. In the bottom right-hand corner, 1919 divided by 1920 is just a little bit less than 1. So I'm going to go ahead and subtract 1 from the denominator. Alright, now I feel pretty confident that px scaled and py scaled go from 0 to 1. If I want the origin to be the middle of the frame, then what was the old origin will then be at -0.5, -0.5. So let's subtract 0.5 from these two values. Alright, let's go ahead and compute RD. I'd like to highlight that given this formula on the right, it's so common that Resolve actually has an implementation for this built in. If we go over to the README, we can see there's a function called hypotf, which returns the square root of the sum of the squares of its two parameters. Given RD, I believe we can now compute XU and YU. In order to square RD, I'm going to be using the powf function described in the documentation. Right here, computing x to the power of y. At this point, we have XU and YU, which are in the same coordinate system as XD and YD. In order to retrieve the undistorted values of x and y in the old coordinate system, we just have to invert this series of steps. Let's start off by adding 0.5 back to XU and YU so that they'll again have the origin in the top left corner instead of in the middle. Next, we'll remove the scaling factor that we had applied earlier to the x and y coordinates. Finally, we have to go back up to our documentation and recall that we have this text2D function that we can use to extract the values in our 3 color channels at this new pair of coordinates. We're going to be saving the result in a float 3, so let's go ahead and make that first though. In the red channel, we'll extract the ptextr, and we'll look at the value that's located at pxu and pyu. Recall that the D in text2D is capitalized. And the first parameter is going to be the texture object. And the next 2 parameters will be the x and y coordinates. Finally, we're going to return this float 3 called out. Okay, let's see if this DCTL runs. I'll copy it into my LUT folder. And this time I've strategically not had resolve running so that we can start it up for the first time rather than restarting. Now we're in our color page and we just have to choose our lens distortion DCTL. Let's see if it runs. All right. We indeed can see some amount of distortion. So our DCTL does appear to work at face value. However, one thing I'd like to notice is that this distortion here is not actually spherical. It's a little wider than perhaps it is tall. The reason our distortion is kind of an oval shape rather than a circle is that we've scaled our x and y coordinates so that the right side is just as far as the top from the middle of the frame. Obviously, for a widescreen format, the right side should be a little bit further away than the top of the frame. There are a couple possible solutions I think we could use. One viable option would be to scale px by the height of the frame instead of by the width. This would result in px scaled potentially going from 0 to like 1.7. Afterwards, in order to offset x to be the center of the frame, instead of subtracting 0.5, we'd have to subtract half of the aspect ratio. Another possible approach we could use is to keep the math here, but then after we compute xd, we would then scale it up perhaps by the aspect ratio so that it goes from 0 to half of 1.8-ish on the right. I can think of other approaches too as to how we could handle this, but let's do the easiest approach, which is to simply scale up xd after the fact by the aspect ratio. We'll start off by computing the aspect ratio. And then we'll simply multiply xd by the aspect ratio down here. At the tail end of our pipeline, we're going to have to correct for this. And that will be all the code that we have to change. Let's see if this looks any better. Let's copy our DCTL over like this and see if that worked. I think this looks a little more reasonable, but let's check it. We do have a grid tool, so we'll go ahead and enter the frame aspect ratio. And then we'll see how that looks here. And we can see that our squares still appear to be pretty square in the middle. I feel reasonably confident that our lens distortion DCTL is doing the right thing. Just for fun, let's try adding one more parameter here. I don't necessarily think that the Y distortion has to use the same parameter as the X distortion. So let's add another parameter for the Y direction. We'll call this one K1X, and then we'll make another called K1Y. We'll apply the K1X to the X direction and K1Y to the Y direction distortion. Let's see how this looks. If we reload the DCTL, we now have 2 parameters. The X1 appears to let us squish the image in that direction. We'll go ahead and draw a grid here. and the Y one allows us to control the vertical kind of squish. I think it might also be useful to have a checkbox in which we can couple these two together. Okay, and what we'll do is we'll see if uniform distortion is checked, and if so, we will use K1X for both of these. Let's see if this works. That seems to be doing the right thing, and if unchecked, we get different distortion properties here. This image looks fine at first glance, but one thing I would like to notice is that if we zoom in, we can see some sorts of jaggy lines here. This is because our text2D call at the bottom is simply doing nearest neighbor sampling, which results in certain aliasing problems. With a little bit more work, you could sample more pixels that are nearby and then do some kind of interpolation between them to get a smoother result. All right, that pretty much wraps us up for today. In this lesson, we covered a simple lens distortion model, and we also covered how to use this other transform function that allows you to do spatial manipulations, operations that can distort or perhaps shift the image within the frame. I hope to see you guys in the next episode of this series.